wraps on that review assignment. And I think we only kind of have one big one left. So that's number 13 on that percent formula. And so one of the things that you need to understand, and one of the most challenging things that chemists have to deal with, is number one, even how do you find the chemical formula for a substance? Because it isn't like we can go, oh, okay, we're going to be dealing with methods or whatever, water, even something simple as water. And we want to find out, okay, what does that look like? Okay? So it isn't like you're looking at a physical structure. So if you were even trying to quote see a water molecule, yes, we represent it as these cute little models, right? Which is actually does a disservice, but it kind of gives us a visual. So again, if you were trying to quote see what a water molecule actually looked like, you would see a very, 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 very tiny nucleus that makes up the oxygen atom. It has 8 protons, 8 neutrons, 8 St. Bernards, 8 sheep bones. And around that, you would just see this cloud, okay, of electrons. So have you ever seen like a fan, like, spinning, and the blade, you have individual blades, but it looks like it's just kind of one big thing because the fans are moving so fast. So imagine those blades are moving close to the speed of light. Okay, what that would look like. So you got this tiny little dot that has the oxygen and proton, the oxygen, the protons and the neutrons. And then you'd have a single tiny, even smaller dot of 1 proton out here that would represent the nucleus of the hydrogen atoms. And then you'd have kind of this distorted cloud around here. Okay, now imagine that shrunk down to something unimaginably small. And you're trying to find the structure of that, and then we're trying to figure out the bond angle in between. Right? Incredibly difficult to do. There's any number of techniques you can do. Most commonly we use like an X-ray, but the X-rays present its own problem. The reason we use X-rays is X-rays have an extremely small wavelength, and the smaller the wavelength is, the better you can see smaller things. But the problem is when you have X-rays, and this is why we use X-rays to look at, when you think you might have broken your arm, because X-rays have the ability to penetrate through bone. So X-rays have an extremely high energy because they have such a short wavelength. So then you're bombarding these things with these really high energy photons, which also has the capacity to distort the electron cloud. So trying to figure out angles and formulas is incredibly difficult. So it isn't like Moses came down and he had like the 10 commandments on one side and all the chemical formulas on the other side, and that's how we knew how that water was H2O. It's like, no, we had to figure this out. So one technique to figure out what things are made of is that you take a sample and you separate it out. Okay, you figure, okay, what is this thing made of? So what's happening on number 13 is that we have the sample. We don't know what the mass is, but we know whatever the sample size is, we figured out that 25.9% of it is nitrogen and 74.1% of it is oxygen. So, important in terms of vocabulary. You have an empirical formula, and then you have the molecular formula. So the empirical formula is the simplest whole number ratio that exists. So here I have like what would be considered an empirical formula. So this is just something simple. It's 1 carbon surrounded by 3 hydrogens. So the empirical formula is literally the simplest ratio. It doesn't necessarily tell you that's the structure. Sometimes the empirical formula and the actual structure are the same thing. But a lot of times they're not. So we might come up with an empirical formula that says it's 1 carbon and we have 3 hydrogens. But then we can use another technique. Typically, one option is, we'll get into this when we do gas laws, is that we actually figure out the molecular structure. And the molecular structure is 2 carbons surrounded by 6 hydrogens. So this ratio is the same. Okay, 1 carbon to 3 hydrogens. That's the empirical formula. The actual structure of it still has that same ratio, but the actual structure is 2 carbons with 6 hydrogens. Okay, same empirical formula, but the structure is completely different. So here's what you got to be able to do. So on number 13, the easiest thing to do is to assume that you have a 100-gram sample of this stuff. Okay? You can say that you have 1,000 grams. You can say that you have 5 grams. It doesn't make any difference. The math is all going to work out to be the same because it's ratio. Personally, because percent means out of 100, I want to say, hey, I've got 100 grams of this sample. Okay? That way I don't have to multiply the percentage by 5 or whatever I want that mass to be, because I just know the percentages. Now, here's the bigger truth of what you're after. And if you keep in mind the end game, the beginning of this seems simple. So what you're after is that you're trying to find this ratio of nitrogen to oxygen. That's what you are trying to find. Now, here's what you have to understand. That this ratio is one of two things. It's either a ratio of atoms or it is a ratio of moles. It is not a ratio of mass. Okay? So you can look at it as a ratio of atoms. You can look at it as a ratio of moles. You can't look at it as a ratio of percentages, as a ratio of squirrels. Doesn't make any difference. You can only work off of atoms or you can work off of moles. Now, if you look at the numbers that you have, okay, you have percentages. I assume that I have a 100-gram mass sample. So what that means is that I'm assuming that I've got 25.9 grams of nitrogen and I have 74.1 grams of oxygen. Okay, that's my initial assumption. Now, because I don't necessarily know what form the nitrogen is in, I don't know if it's a gas, I'm just assuming that it's going to be elemental nitrogen. Okay, and so what I want to do is convert those grams into moles. Okay? So, do not make this complicated. You're not necessarily told that it's nitrogen gas or that it's oxygen. You're just told that it's nitrogen and oxygen. So, odds are it's going to be that form, but you weren't specifically told that. So you sit here and go, okay, hey, I got 14 grams of nitrogen. I've got 16 grams of oxygen. Okay? So what that allows us to do is figure out how many moles of this stuff that you have. So you do this math, you get 1.85 grams of nitrogen, and you get 4.631 grams of oxygen, moles. Now, here's where you step back. Okay? You stop right now. On these coefficients, since I've got 4.631 moles of oxygen and 1.85 moles of nitrogen, which of these numbers, those subscripts, is going to be bigger, the oxygen or the nitrogen? The oxygen, because I have more moles in this stuff. So I know whatever goes here with the oxygen has to be bigger than whatever goes with the nitrogen. Okay? So start with that idea. All right? Okay, I don't know what I'm going to end up with, but I know my oxygen has to be bigger than my nitrogen. So this is a ratio. So you take the 4.6 to 1 and you divide that by the 1.85 moles of nitrogen, and you get 2.5. Now, beyond just the number 2.5, what this means is that I have 2.5 moles of oxygen to every 1 mole of nitrogen. Okay? It's hidden within that, but that's what you got. You got moles of oxygen, 2 moles of nitrogen. So I could come in here and go, oh, okay, that means this is 1 and that's 2.5. But why is that problematic? Can't have a hat. Okay? Can't have a hat. Bad. So what can you do? Double it. Okay? So then, so you can either double this if you're more of a mathematical, I love fractions. Nerd. So you can also look at it, that's hardcore, man. If your chemistry teacher is calling you a nerd, that's hardcore. So if I do this, I multiply 2 by 2, I get 4, I get 5 halves. So this is a deeper truth. The advantage of this is that it shows that true ratio. Oh, this means that I got 5 moles of oxygen to 2 moles of nitrogen. Okay? So the beauty of changing it into an improper fraction is that it does actually show that ratio of 5 to 2. Okay? So now I can come over here and go, okay, cool. I've got n2 O5. That's my empirical formula. All right? Cool. You have that number. Now, here's how you can check if you got this right. Work backwards. Take, if you really wanted to, if you wanted to see this is right, take your N2O5, find the molar mass of N2O5. Take 2 times 14, 5 times 16, take the mass of your nitrogen divided by the mass of your total, and see if you get that percentage of 25.9. If you did, you probably did it right. If you didn't, I promise you it's wrong. Okay? So that's just a simple way that you can check and go, hey, did I do this right? Now, the next part says the compound from the treatment has a molecular molar mass of 216 grams per mole. So what we're saying now is that when you look at the entirety of this molecule, and typically this is easier to do with gases, and you'll see that math later on, we end up and we realize the molar mass is 216 grams per mole. Okay? Cool. So what you know is that just like the molar mass of this would be 12 because I got a carbon, and I got 3 hydrogens around here, this would be 15. So the molar mass of this would be 15 grams per mole. The molar mass of this, because I'd have 2 carbons, that would be 24. And then I've got the 6 hydrogens, it would be 30. So the molar mass of this is 15. The molar mass of this is 30. So that means that it's a 2-to-1 ratio. So if I can figure out the ratio of the molar masses, now I know what I need to multiply my coefficients by to get to that value. So here's what you're going to do. Find the molar mass of N2O5. Okay? Take 2 nitrogen, 5 oxygen. So the molar mass of N2O5 times some multiple is going to equal 216 grams per mole. So once you find the molar mass of your N2O5, take 2 times 14 plus 5 times 16, you're going to get a number. Divide the 216 by the molar mass of your N2O5, that's going to get you a ratio. Okay? Now, if you do that ratio and you get something weird, like 3.5 or 3 1/3 or 0.8, you've done something wrong. Okay? This step, if you've done the previous steps right, this will always work out to be a whole number or something very, very close to a whole number. So if you do this step and you get a fraction, something's gone horribly wrong. So here's how you can check that your final answer is right. Whatever you think your formula is on that last one, that ratio of nitrogen to oxygen, there's a couple of things you could do. One is you could, when you get that final answer, find the molar mass of that and see if it's 216. If it is, hey, odds are you did it right. If you find that molar mass and it's not 216, something's gone horribly wrong. You could also take what you have as that final answer, do the percent composition of that final answer. If that percent composition matches up to be 25.9 and 74.1, again, odds are you did it right. If you didn't, it's a train wreck. Okay? All right. Are we cool with that? Anything else on that big review assignment? Finally, we get to turn that in. So you guys will hand stuff in on that second tray down. There's labeled AP Chemistry on the outside of it. Okay? So if you have it, if this sounds weird, but it's going to be true because old habits die hard. I'm not worried about you, Natalie. But if I've had you for other classes and you're used to handing it in either into the top tray or that third tray down, old habits die hard. Make sure that you're handing it into the AP Chemistry. Okay? So get that handed in.